$6 million produced a model that matches what cost more than $100 million to train. Export controls blocked the most powerful NVIDIA chips from reaching Chinese engineers, so those engineers optimized their way around the constraint, and the optimization was the breakthrough. The metric is training cost per frontier-class model. The then reading comes from the American side of the ledger, the now reading comes from Shenzhen, and the delta between them has rewritten a core assumption the chip industry was built on. Training cost per frontier-class large language model is the instrument. One number, denominated in dollars, attached to a dated training run, benchmarked against a named performance tier. The then reading, more than $100 million, which is the analyst range consensus for what OpenAI spent training the model it released in March 2023. OpenAI has never published an audited cost breakdown, so treat that figure as a directionally reliable estimate built from cluster size calculations and publicly available chip-hour pricing, not a confirmed total. The now reading, approximately $5.5 to $6 million, which is what the Shenzhen-based lab DeepSeek disclosed in its technical report published in January 2025, covering the training run it completed in late 2024. That figure is the company's own disclosure and covers compute cost as the company defines it, meaning chip hours at the rates DeepSeek pays internally. It does not include the months of failed experiments, the engineering salaries, or the infrastructure costs that do not appear as line items in a technical report. The true all-in cost is higher. The compute figure is real and the methodology is documented, but it is a floor on one component, not a total project budget. With those caveats attached to both readings, the gap is still enormous. More than 100 million, approximately 6 million, a reduction of more than 90% across roughly 20 months. The mechanism that produced that reduction runs through the hardware. The export controls the United States imposed did not simply remove the best chips from the equation, they replaced those chips with a specific, deliberately degraded alternative. NVIDIA's H800 carries the same processor core as the H100, which was the chip most frontier labs were building their training pipelines around. The H800 was reconfigured specifically to comply with export rules by reducing the bandwidth of the connections between chips, the pathways that let processors communicate with each other during training. That interconnect bandwidth is not a minor specification. It is the bottleneck that large-scale training runs strain hardest, because coordinating gradient updates across a large cluster requires chips to exchange enormous volumes of information continuously. DeepSeek's engineers were handed a chip that was slow in exactly the ways that matter most. They did not receive inferior hardware by accident. They received hardware that had been engineered to be inferior in a targeted way, and they built their training pipeline around that specific constraint. The pipeline they built restructured computation so that chips spent less time waiting for each other and more time computing. The architecture they chose, a mixture of experts' design, means the model routes each computation to a small subset of its parameters rather than activating the full model for every input. This reduces the volume of information that needs to move between chips during a given training step. Fewer bytes in transit means less time spent on the hobbled interconnect. Alongside that, they applied aggressive quantization, reducing the numerical precision at which values are stored during training. Lower precision means smaller numbers mean less memory consumed, and less memory consumed means the pipeline can move faster with fewer chips. Neither of these techniques was invented by DeepSeek. Both had been documented in the research literature. What DeepSeek did was build an entire training pipeline around them, from scratch, under hardware pressure, with no fallback to a faster interconnect when the bottleneck appeared. The cluster that produced the result was 2048 H800 chips. A cluster of that size fills roughly the footprint of a large conference room, not a purpose-built hyperscale data center wing. That physical plant, a single large room's worth of hardware, ran for approximately 2 months and produced a frontier-class result. The chip count matters because frontier model training at the tier DeepSeek was targeting had been broadly understood to require clusters of tens of thousands of the most capable available chips. The numbers discussed in the context of comparable training runs ran into that range. 2048 is not a rounding error off that figure. It is a different order of magnitude entirely. The hardware footprint shrank by more than an order of magnitude relative to what the frontier assumption had been. The 2 months of wall clock time compounds the cost reduction. Large frontier model training runs had been understood to take many months on large clusters, with timeline estimates ranging from several months to approaching a year depending on cluster size and configuration. 2 months on a smaller cluster means fewer chips running for less time. The cost is the product of both. Efficiency gains in how gradient updates were communicated across the cluster reduced the time each chip spent waiting rather than computing. The hobbled interconnect, which looked like a pure disadvantage, forced engineers to restructure computation so that the waiting happened less often. The constraint produced the optimization it was intended to prevent. The fourth measurement is the one that unsettles the underlying model most directly. DeepSeek 5.3 scores competitively with the models it is being compared against on coding and reasoning benchmarks, and less uniformly on others. Benchmark parity is task-dependent, and frontier class is a range rather than a binary. The specific tasks on which two models are compared matter for how broad the performance claim is. What independent evaluations from researchers who ran the model confirm is that the performance gap closed without the cost gap closing. The two readings that had been assumed to move together, capability and expenditure, decoupled. That decoupling had been treated as structurally impossible because the same labs were advancing both variables simultaneously. A lab that is forced off the standard hardware stack and must re-engineer from scratch breaks the coupling by accident because it has no choice but to find a path that does not require the expensive hardware. A water utility that loses pressure at the main does not lose water at the tap by the same proportion. It re-engineers the local distribution network with smaller pipes, better routing, and less waste at every junction, and sometimes ends up with a more efficient system than the one running on full pressure ever produced. The H800's reduced interconnect bandwidth was the pressure drop. The re-engineered training pipeline is the local network that came out of it. Three interpretations sit underneath the delta, and they do not all point in the same direction. The first is that the export control modeled the wrong variable. The restriction was designed around the premise that raw interconnect throughput was the binding constraint on frontier model quality. If you slow the chip-to-chip communication, the reasoning went, you slow the training run, and if you slow the training run enough, the cost makes the result unachievable. What DeepSeek's result shows is that interconnect throughput was not the binding constraint on model quality. It was a constraint on one approach to training. A different approach, rebuilt from scratch around the constraint rather than despite it, found a path that the export rules designers had not modeled. The second interpretation is that this is not primarily a story about the cost of Chinese engineering labor. Chinese engineers are not cheaper in the way that Chinese manufacturing labor is cheaper. The cost difference is not driven by lower salaries per compute hour. It is driven by algorithmic efficiency, a different architecture, a different training pipeline, a different set of choices about what to optimize under hardware pressure. Those choices are now documented in a public technical report. They have been read, replicated in part, and absorbed by researchers at labs on every continent. The efficiency methodology has already propagated beyond the organization that produced it. An export restriction can control the movement of physical chips across a border. It cannot control the movement of a documented training technique across the internet. The third interpretation concerns the pricing model of the chip industry at the frontier. That pricing model rests on one premise, that the most capable models require the most capable hardware, and that the most capable hardware is expensive enough that only a small number of organizations can afford the clusters necessary to train at the frontier. DeepSeek 5.3 does not merely challenge that premise in the abstract, it provides a dated, reproducible counterexample with a public methodology attached. A competitor with better chips can be managed through export controls, through supply chain pressure, through the leverage that comes from controlling the manufacturing of the hardware itself. A competitor whose efficiency advantage is architectural and documented cannot be managed the same way. The architectural insight has already cleared every border it will ever need to cross. The caveats belong here, attached to the readings rather than presented separately. The $6 million figure is a floor on compute cost, not a ceiling on total expenditure. The $100 million figure is analyst range consensus, not an audited number, and the precise ratio between the two is uncertain even if the order of magnitude gap is not. Benchmark parity is partial and task-dependent, and calling DeepSeek v3 a full equivalent of the models it is being compared against overstates what the evaluations confirm. And one data point is a reading, not a trajectory. The cost compression may reflect a one-time architectural insight that has already been fully absorbed and will not compound further. Or it may be the first reading of a new cost curve. The second reading, when it arrives from a subsequent training run, will carry more information than this one does. The readings are real, the delta is real, the mechanism is documented, the uncertainty is in the magnitude of the precise gap and in whether the trajectory continues, not in whether the gap exists. The instrument shows this. The metric moved more than 90% in the direction the restriction was supposed to prevent over roughly 20 months. Using hardware the restriction deliberately degraded. The assumption priced into the chip industry's business model at the frontier that capability and cost are coupled and that controlling the most expensive hardware controls the capability now has a dated counterexample attached to it with a public methodology and a result that other labs have confirmed independently. The restriction was designed to freeze a capability metric. It moved the metric instead because the ceiling forced the engineering, and the engineering is now documented, distributed, and replicable by anyone with access to the technical report and a cluster that fits inside a large conference room. The wall did not hold the number. The number learned the wall. The next dated reading to watch is any frontier-class model released from a Chinese lab or a Western lab applying DeepSeek's documented techniques in the second half of 2025. If a model at that performance tier trains below $3 million before the end of that year, the cost compression is a trajectory. If the cost floor stabilizes around where it is now, this was a single data point, a sharp one, but not yet a confirmed trend. The instrument is still running. When the next reading lands, the gap will either be wider or it will have closed, and that gap will tell you more than this one can. If you want to be here when that number comes in, subscribe and turn on notifications so the reading actually reaches you.